Hi there everyone, this is Penelope and this is topic 13 class 2, the second of the videos on complex numbers. And today we're going to be looking at Argon diagrams and putting a complex number into polar form. Now, often if we can see something, it's easier for us to understand. So if we can see a complex number, we can kind of get the idea. They're called Argon diagrams because they were named after a guy, Jean-Robert Argon, but he lived a long time ago. This is not modern stuff. He died in 1822, so it's not new stuff. What we can do is if we have a complex number, say z equals a plus ab, that would be a in the real direction and b in the imaginary direction. But if we can find the length of that and the angle, then we could draw it differently. We could say, okay, it's at angle theta and its length is, say, r, and then we could just draw that without having to know the length in the horizontal and the length in the vertical. We would then find them, they would show up, but we could find it in this alternative manner. So we talk about r being the modulus, or the length, or the magnitude. So this is the modulus of the complex number, or the magnitude. And we write it like that, or sometimes you see it written as mod z. The way to work it out is just by Pythagoras. So we've got a line like that. It's just the hypotenuse of a triangle. So the modulus would be equal to the square root of a squared plus b squared. Theta is the angle that makes, and that is called the argument of the complex number. And we would find that, again, by any triangle. If this is a and this is b, then theta would be that angle in there, and theta would be the inverse tan of b over a, being the opposite over the adjacent. Nothing new there. Have a look at these examples. The first one, we could find the modulus. The modulus, remember, was the square root of a squared plus b squared. So we're looking at this complex number, so we can find that r is the square root of 1 squared plus 1 squared, which is the square root of 2, which we kind of know because it's a 1-1 triangle with root 2 as the hypotenuse. And we could find the angle, so theta is equal to the tan inverse, the inverse tan of opposite over adjacent, which is 1 over 1, which means it would be 45 degrees or pi by 4. If we look at the third one, where we've got z equals -1 plus 0j, then the length is going to be the square root of 1 squared plus 0 squared, which would be 1, and the angle will be the inverse tan of 0 over -1, which is 0. So our angle is either 0, which it can't be, or pi. And that's that length in there. So its length is 1 and its angle is pi. Now, we can find these using the calculator. If we're looking at the first one, what we would do in our calculator is we would type in pole. We'd find the pole button, then we'd type brackets, 1, 1, and that would give us that r was equal to 1.414, which is the square root of 2, and it would give us that theta was pi by 4, or the decimal equivalent if we had it in radians. So if our calculator was in radians, that's what we would get. If our calculator was in degrees, we'd get 45 degrees there for the angle that it makes. Now, looking at this diagram here, we have 5 plus 3j as being that one there. So what we're going to do is we're just going to type in pole 5, 3, and we would get that the length is, well, you'll get a number. The length would be 5.831 would be the length, but I'd really prefer it that you wrote that it was the square root of 5 squared plus 3 squared, which is the square root of 34. Now, the angle we would just read off, it would be, if we've got it in degrees, it would be 31 degrees, or if you were working it out, it would be the inverse tan of 3 over 5. And the same as the others, you could find them using the rules, or you could use your calculators. Now we can write that as r angle theta. So we read that as z, our complex number, equals r, which is the modulus, angle theta. And we've already done that one. Now, just drawing it on an ordinary set of complex coordinates, we've got the real axis, we've got the imaginary axis. Now, just normal stuff, we can work out that cos theta is equal to x over r, and the sine of theta is equal to y over r, just normal stuff. So that means z is equal to r angle theta. The imaginary parts and the real parts we can work out in polar form, so that x would be equal to r cos theta and y would be equal to r sine theta. So we can get them from there, or we can use the calculators. So it means that we can write z is equal to x plus jy, which is, all of these are the same thing, which is r times cos theta plus j times sine theta. Now, if we had the complex conjugate like that, then we would write that as r times cos theta minus j times sine theta. Now, you don't have to work these out. You can use your calculator if the question just says, you know, what are we looking at here? Now, Cartesian form is where it is a plus jb. We could use the rules on the previous slide, or we could just use our calculators. And let's use the calculator. So we're going to convert it to rectangular, so that would be shift rec, and we'd enter in 4, 30 degrees, making sure that our calculator was in degrees. And then we would get that our x length would be 3.464 plus 2j. And we could do the same with 7 angle negative 145 to find the x and the y. We would type in REC bracket 7 comma negative 145 with our calculator in degrees, and that would give us the x length and the y. Now, the reason for doing this is that it makes multiplication and division so very easy. To multiply, we multiply the r's together, and then we add the angles. So if we've got the example there, 3 angle 25 times 4 angle 60, that's going to be 3 times 4, which is 12, angle 25 plus 60, 85 degrees. Division, before we had to multiply by the complex conjugate or use the formula. This time it's so easy. It's going to be the moduluses divided by each other, angle, and then the degrees, the angles subtracted. So if we've got the example there, 16 angle 75 over 2 angle 15, that will be, what are we going to do? We're going to do 16 divided by 2, which would be 8, angle 75 minus 15, which would be 60 degrees. Now, if we think about how we could expand that, an extension of that would be that if z is equal to r theta, then z to the power of n, which is z times z times dot 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 z, would be equal to r to the power of n angle n theta. And that's a very famous theorem, DeNoirs Theorem, and it's very, very useful. Now, we can do really complex ones. We can do 4 angle 2 pi over 3 squared times 3 angle pi by 6 squared divided by 5 angle pi by 4. And if we do the top line, we get 144 angle 5 pi by 3. And on the bottom line, well, that's still the same. And then if we do the division, 144 over 5, well, that's just 144 over 5. And then we do the subtraction of the angles, 5 pi by 3 minus pi by 4 would give us, we have to use fractions, 17 pi by 12. Now, before you do the test, those of you that are doing my course with the MyMathLab questions, just make sure you have a look at these questions first. There's nothing really difficult about this one here. You just have to put the numbers into the formula. The second one here, that's just how we write those. You might get that question there. If it asks you to write it in trigonometrical form, it's just cos 5t and j sine, that's a 3 actually, 3t. If we're going to write the exponential form of negative 3 plus 5j, first of all, put it in polar form, and then you get that r is equal to 5.83 and that theta is equal to 2.1. Similarly, this is the rule for finding that. And last but not least, use the DeNoirs Theorem on the previous slide to work out that one. One final question. It looks complicated, but all you have to do is put the numbers into the formula and work them out using your calculator. Not difficult.